In this video, you'll watch a live class that I ran for my students, which is effectively a review of all the key concepts from functions and relations. Enjoy. Okay, might as well get started. Cool. So, here, since you just joined, basically all we're doing here is to go through a review chapter of everything that is functions and relations related. We'll do a few key questions and then we'll it won't stick around in any one particular spot for too long, as long as we're getting through unique questions. Cool. So first things first, from a screen share, you know what, I'll even copy some down, just the handwritten notes. That way we can work off of just one screen. But the first question is to do maximal domain and range of certain functions. So maximal domain we have is a function f of x is equal to 1 over x plus 2. So when we're talking about maximal domain, it simply means all the possible x values for that function. So really the easiest way to go about these is to figure out what would be the restriction, like what x values can't I put into this, and then your domain is going to be everything but that. So what x values would cause this to break?
X equal to 0.
X equals 0. Cool. So if that's the only issue, then what might we put in as our maximal domain?
X can't equal 0.
Yeah, x can't equal 0. Nice. So you would say for maximal domain, if you wanted to be really formal about it, you'd say x is an element of all real, excluding 0. That'd be domain. Real quick, welcome Cheyenne. We're just doing a review of all function and relation stuff. So this could be anything from the square root graph, polynomials, basically all that sort of stuff. Okay, so that's domain for this function that we have here. Actually, Cheyenne, this might be your first. Just a brief review. I've got a bunch of screens going on, so if you can click through all the different screen shares, the main one we're going through is going to be the handwritten stuff. I'll just copy some questions down onto that. But okay, so that's domain for this function f of x. What's the range of that going to now be? Bit tougher of a question. Usually requires a bit of a quick hand-drawn sketch to get an idea.
Would it be y is equal to 2?
Y equals 2 will be the only value that you can't have, because that's where the asymptote would be. So if you were to draw a quick version of this graph, it's been shifted up by 2, and since it's a hyperbola, it'll do that, essentially. And so when you think about the range being all the possible y values there, then essentially what you're saying is all real numbers excluding 2 for the range. Is that clear?
Right.
So you might say something like y is an element of all real excluding 2. Using those squiggle brackets because squiggle brackets indicate individual values, whereas if you had rounded brackets or square brackets, you're indicating an interval. But okay, that's that. Next up that would be unique would be a square root graph. So let's bring one of those up. I'm going to have f of x is equal to 3 minus 2 root 3x minus 2. All right, maximal domain and range of this one. What are we going to do?
Would we like bring the 3 to the other side so we can easily see the y translation?
Yeah,
Not to the other side, I mean like we just put it like plus 3 to the back of the square root.
Oh, yeah, sure. Okay. Yeah, that's fair. F of x equals minus 2 root 3x minus 2. And you can put the plus 3 there instead. Yeah, that makes it a bit clearer to see what's going on. Sure. All right. Maximal domain and range of that, though. If we're not super clear immediately, how could we at least get closer?
Would x be all negative numbers, all negative real numbers?
Okay, so we could even test some of that. So if I were to put in, like, let's say x equals -10, do I have a good value? So we're going to have -2 root, well, -10 times 3 is going to be -30. So you're going to end up with an issue of root -32, which is unfortunate. So not all negative numbers. Pia had the right idea, which was, could we make the square root bigger than or equal to 0? Because what you want to make sure is that anything that's inside the root is a positive or 0. So maximal domain is always going to be setting this to be greater than or equal to 0. That's the bulletproof way of doing it. So 3x minus 2 greater than or equal to 0. X is greater than or equal to 2/3. The other way to do it would be to identify what our function looks like and what the horizontal translation is. Because if you were to take, for instance, a factor of 3 out from here, you would have f of x is equal to -2 root 3 bracket x minus 2/3. And then suddenly you can see that because you're being shifted right by 2/3, you know that everything to the right of 2/3, including 2/3, is also good. So 2 different ways to get to the same goal. Okay, so that's maximal domain there. And then as for range, how do we go about that?
Would we have to sketch it to figure it out?
Yeah, I mean, you don't have to necessarily sketch it. If you can eyeball it and say this is shifted up by 3 and this negative means it points down, then you can use that information alone to do it. But yeah, doing a quick sketch is no real issue if it's unclear. So for sketching square root graphs, one of the things you need to know is where it starts. So based on the information we have available to us from here, how do you know the starting point?
The endpoint being 2/3, 3.
Yeah, 2/3, 3. 2/3 because this means a shift right by 2/3, and this over here plus 3 means a shift up by 3. 2/3, 3 up here. That's our starting point. You can call it a vertex, starting point, doesn't really matter. I don't think it has a specific name. If you were to give the more accurate one, probably vertex because it came from a parabola. But either way, what do you do from here now to get the overall shape from it? How do you know which way it's going?
You look at the negative symbol.
Yeah, negative symbol. So that negative symbol being up here, what does that tell you about it? Is that going to cause it to go left or go down?
Reflected across the X.
Yeah, across the X or go down. Both of those are, yeah, the same. So across the X, this being the X, it's going to shift like that. That's really all we need. You could, if you were trying to sketch it, grab that X-intercept, but because you only care about all the possible Y values, you just want a picture. So looking at this graph, what must therefore the range be in this case?
-infinity to 3.
Yeah, -infinity to 3. What brackets are we putting around those?
The -3, the minus infinity will be like circle
Yep.
bracket, and then 3 would be included.
Perfect. 3 is inclusive. Nice. Absolutely. Okay. So that's pretty much everything that's unique from question 1. There are other functions. One thing I do want to touch on that's still in question 1 would be a function you haven't seen before, but you should still be able to get an idea of how you might handle it. So something like this is what we have as a function. The only thing I'll ask about this is its domain. So how might we go about finding the domain of this? We've actually done it before, even though this looks a bit different. The same procedure applies.
Would we make it bigger than or equal to 0?
This is still a square root fundamentally, and so everything inside the root, no matter what it looks like, has to be greater than or equal to 0. So you want this to be greater than or equal to 0. Now, does anyone know how to solve this? There's a couple of ways you could do it. Any thoughts on how you could go about that?
Would you square the y and then solve on the right side to get like a circular function? Circle function.
Square both sides, okay. So we've created this equation. So you're talking about going back to this, squaring that, and then.
Oh wait, were we talking about the second line?
The second line, yeah. This is what we're up on.
You just use null factor law, I'm guessing.
Yeah, so null factor law is a way that you could do this. That will tell you the breakpoints for which you equal 0. So very quickly, x equals 2 or x equals minus 4 will equal 0, but you want to know where is it greater than or equal to 0. Bit tougher. So that's a good start for the null factor law approach. What can we now do to figure out what values would also be greater than 0? I will say this is probably the tougher way to go about it, but still doable. So if there's no ideas, I'll jump in about a minute.
Would you be able to just repeat that question, please?
Yeah, so what we found here so far is x equals 2 and x equals negative 4 is going to be when this function is equal to 0. But we're not trying to do exactly equal to 0. That's part of it. We want to know where is it greater than or equal to 0. So these will be useful in the answer, but they are not the final answer. What could we potentially do to figure out when are we greater than or equal to 0?
Would you expand the brackets and solve for 0? Solve for x?
So that's actually what this would achieve. So expanding the brackets, solving for x. Well, expanding the brackets for a quadratic is kind of tough. You would have to then do a quadratic formula from that. Still, even if you were to do that, expand all the way out and then solve, you would just get back to x equals 2, x equals minus 4. The way you handle it through a null factorial approach when you're doing inequalities is you use, I think it's called sign analysis. Basically, because you've got two things that are multiplied together, when we're saying greater than or equal to 0, we're basically just saying positive numbers or 0. So we've already figured out the 0 part of it. The next thing is, what would it take for this times this to become positive? And there's two answers. Either both of the terms are positive, in which case you get a positive, or both of the terms are negative, in which case they cancel back down to being positive. It's kind of tough to do that. So basically you're looking at what would it take to make this and this positive at the same time, and what would it take to make this and this negative at the same time. So very briefly, you'd have x minus 2. This will be positive if x is greater than 2. It'll be negative if the opposite, x less than 2. So technically not including 0, but point being. And so you just do that for both terms and then look at the intersections between those two things. It's kind of complicated, I would say. So my preferred approach is to simply graph this. This is just graphing a quadratic. You've already done the null factor law on this, which is part of the solution, giving you x equals 2 and minus 4 as your intercepts. Then from there, to get the overall shape of the graph, you're just saying, is this a positive or negative quadratic? it is of course a positive quadratic. Now, from here, you want to know where is this quadratic greater than or equal to 0. That just means the y values, because this is a sketch, the y values of that quadratic, where is this above the x-axis? That's going to be everything right of here and everything left of here. So a much easier way of doing it rather than doing this sign analysis stuff. Both works, it's just this is the preferred approach. So final answer, you'd say something like x is an element of negative infinity to negative 4 inclusive, because you want to include the 0, union 2 inclusive to infinity. So basically, whenever you're trying to do some polynomial inequality, make the inequality be about 0, sketch that polynomial, and then look. If it's greater than, you want to be above. If it's less than, you want to be below.
Could you also say that like x is an element of R, but like excluding -4 and 2?
Yep. So you're just going to be mindful of the brackets that you use there. So you could say x is an element of R, excluding, now we know it's between negative 4 and 2, but because we're excluding, we now want to put circles on these, where previously we would have put thingos. Difference being, this is saying what you include, this is saying what you exclude. We want to include the negative 4 and the 2. So in this case, because you're saying exclude, you want to put a round bracket on it. So that's the only nuance there that's worth discussing. It's kind of why I prefer doing this top one. Even though it's a bit more wordy, it's at least more intuitive. Personal preference though. Cool? Okay, that is that. Next up, we've got an inverse function. So let's quarantine that off. I'm going to have some function f of x is equal to root x minus 2 plus 4. All I care about for this is that you can find the inverse. So how would we find the inverse of this?
Well, you just sub in f of x as the x, and then like the x of y, just so.
Yeah,
I mean,
so that,
y.
yeah, okay. That did come a bit foggy, so I'll just repeat it for everyone else. That was, you rewrite f of x, so y, as x, and you replace every x with a y. That's always stage 1 of the inverse. And then stage 2 is getting that y back on its own. I'll just rush through at least the basics of that. So you subtract 4 from both sides, you would then square both sides, and then get the y back on its own finally. X minus 4 all squared plus 2. Those are the basics there. Now, part of the inverse is that you also have to care about domain and, well, just domain, really. So, any thoughts on how we can find domain of this function? While you think about that, I'll be drawing a little picture to hopefully help out. The key thing I'm trying to illustrate there is that when you do the inverse of a function, what you're doing is reflecting in the line y equals x. So to demonstrate that, I've plotted f of x in the solid dark line, and I've plotted our inverse in a bit of a shaded, lighter white line. One of the issues we're seeing there is that these are not the reflections of each other, at least not yet. What's wrong with this that makes it not a perfect reflection?
They aren't the same.
Well, yeah,
Like
they aren't the
as,
same, for sure.
as in like the definition of the function or the shape of the function.
Yeah, the shape. So we've got a parabola. So there's only one portion of this that's actually the bad portion. And that is, so if you were to do like the perfect reflection, it would be, you'd want this bit. Because then, I mean, I know it's not great because I hand drew it, but if I sort of tilt that on its side there, if you just cared about this and this, those are supposed to be perfectly reflected either side. So you've got this portion over here that's bad. Well, not necessarily bad, but we don't want it as part of our drawing. So one way of figuring out the net domain or the new domain of your inverse is simply sketch and then look, like which one do I actually want to keep? Which one would make this work? And to make this work, you'd have to restrict your domain from 4 to infinity for the inverse. So your inverse therefore has 4 to infinity and a b inclusive. That's one way of doing it. The other is the global rule for all inverse functions, and that is simply that whatever the domain and range of your original function is, become the range and domain of the inverse. So they flip. So one way of doing it would be, what is the range of this? So if you see that dark line, you start at 4, you shoot to infinity. That is the range of f. It has become the domain of of the inverse. Is that clear enough? Why we have to cut it off like that? Okay. And I guess I have kind of done the rest of question 2, which is sketch them. Okay, question 3 is just another inverse with a different function. We'll skip that. Only thing I'll touch on in 4C will be, yeah, okay. So sometimes you'll come across something like this. Y equals f of f inverse of x. This has a very specific rule that it always comes out to be. This is more of a memory thing. Does anyone memorize or remember what f of f inverse x is always equal to, regardless of f or its inverse? Yeah, okay, that's fine. So whenever you do f of f inverse, it will always be equal to x, no matter what the function is. It even works if you do the opposite way. So f inverse of f. Now, a slight nuance on that, as is being depicted in part E of the question, is what happens if I have, let's say, f inverse f of 3x. What do I do there? Well, the nuance on that is whenever you have a composite function with its inverse, whatever's in the brackets in the middle is what that will always simplify down to. Now, that's only part of the question that's being asked here, which is what is the rule of that, in which case you give x, or whatever that ends up looking like. The next part is what is the domain of these functions. So these functions are going to have different domains. We can ignore this one, that was just a hypothetical. When we think about how composite functions work, they work like this. You start with some x value, it gets fed into whatever the inner function is. So for our purposes, just so we can keep it generic, we'll say we have f of g of x. The inner function is g of x, so x value gets fed into g. From there, g produces some y value, which gets fed into f. And then at the very end is when you get your y value out of your composite function. This box here is your composite function. This at the front is the domain of your composite function because it's all the x values that come into it. This at the front is the range of your composite function because it's all the y values that come out of it. So the reason why these have the same rule but will have different domains is because I have a different inner function. If you think about how everything comes through, x has to get into the inner before it can get through the rest of the function. So if I have a different thing here, then my domain must therefore change. because the domain of your composite function is always the domain of the inner, whatever that looks like. So depending on what functions you have, you'll have a slightly different domain associated. We can do just a decently easy-ish example of it. Let's say we have f of x equals, oh, you know what, we can even just use the same one, why not? 2e 3x minus 1. We've already talked about how you would find the inverse. You just swap the x and y, and then you rearrange for y. It's going to give you x plus 1 all over 2 equals e to the 3y, and then converting to a logarithm is what you would have to do here, which means you're going to have a base of e, so natural log. Whatever's here goes inside the brackets, and then whatever the power is comes out here. If it's been a while since you've done logarithms, that is just a stock standard swapping of the terms. That's something you're just going to have to practice. And then finally, y equals a third, 1 over 3, natural log x plus 1 all over 2. Okay, so that therefore is going to be our inverse, so f inverse of x. Now, we weren't given any, like, oh, we kind of actually were actually. This did have a domain of all real. If we think about the rules for inverses, domain of this is going to be range of this. So, because we've already done this a bit before, I'll just briefly say the range of this is -1 to infinity. So I'm going to say, in this case, x is an element of -1 to infinity. And non-inclusive. Okay. So I'm speeding through this just to show you that when you have f of f inverse of x, that equals x, but it's going to have the domain of the inverse. So it's going to have this. X is an element of -1 to infinity. If you had f inverse of f of x, that will still equal x, but it's going to have the domain of this, which is all real. So when you sketch both of these graphs, they're still going to be basic linears because it's just x. This one you're sketching from -1, that should be an open circle, -1 to infinity. This one you're sketching as just y equals x because it's all real numbers. Do I need to clarify the difference between when you use what domain? Okay. Oh, I think I heard something. Was that a question?
No, I was just saying like the time.
All good. Okay, so next up, just some basic log law stuff. Well, I say basic. It might have been a while since you've seen it. You have 2 log 10 5 plus 3 log 10 2 minus log 10 20. All right. So this is stock standard log laws. Does anyone recognize what you do to simplify logarithms that look like this? There's 3 laws that are in play, that are at play here. In fact, while you have a think about it, I'll even bring up the notes of the log laws that apply. And you can ping back and forth between the screens. All right, everything you need for this question is on the screen share. Logs you add, you multiply, subtract, divide. Yeah, exactly. So the ones that get added, the idea being that you take whatever is in the brackets and you multiply them. When they subtract, it is a division. So if I were to do just this one, you'd have, now not quite, but you'd have 2 divided by 20. Now there is something here that's blocking us from doing that immediately, and that's these coefficients. All right, we're having some issues there because those coefficients make life a little bit harder. What can we do to make it more able to use those log laws? There's another one that's on the screen share. bring them to power, precisely. So for everyone else on the screen share, if you have a coefficient out the front of a logarithm, that can be brought in as a power of the entire bracket. So you're now going to have log 10 of 5 squared plus log 10 of 2 to the 3 minus log 10 of 20. Now we can use as additional log laws. So the addition means they condense down to the multiplication of those two things. So you're going to have log 10 of 5 squared times 2 to the power of 3. And that subtraction means you're going to divide everything by 20 at the end. Now, that's just some number. We know how to simplify these things. I think I'll leave that as that. Point being, that's how you use logarithm laws. Okay, let's see. Have we got anything else unique? Kind of unique. Yeah, okay. Next one up, some exponential stuff. So we have a function that is 2 times 2 to the minus x is equal to 1024. What might we go about doing here to solve for x?
Try bringing 1024 to like the base of 2 and like the power.
Yep. Just to repeat that for everyone else, we're going to rewrite 1024 as a base of 2. Now, knowing your powers of 2 is pretty handy for these kinds of things. If you're not familiar with your powers of 2, then you should play a game called 2024. Sorry, what is it called again? 2048. That's what it is. Literally type this in Google. It's like you'll find it on like cool math games or something like that. You'll learn your powers of 2 pretty quickly, and it'll be fun. Very quickly though, you got 2, 4, 8, 16, 32, 64, 128, 2, 56, 5, 12. So that's power of 10. 2 to the 10 equals 2 to the 2 minus x. I know that because I've done engineering and all sorts of shit. We'll ignore how I got that. Just play this game. You'll learn. Okay, that's a good start though. Where do we go from here?
Would you equate negative x to 10, like negative x equal 10?
Pretty
'Cause
close.
The base is all the same.
Yeah, that's super close. The only thing is you've got this multiplication of 2 that's in there. How do you handle that?
Would it be negative x plus 1?
Yeah, because you condense that down into 2 to the minus x plus 1, and now you say minus x plus 1 is equal to 10. And then you get x on its own pretty easily. Nice, yeah, so for everyone who's a bit still unsure, the way you handle these is you equate exponents, which means get everything down to the same base. Once everything is in the same base, you can then just look at the exponents specifically and then solve those individually. Okay, that's that. Let's see, is there anything else unique in here? Yeah, let's get some. Yeah, we'll hit the circular function one first, and then we'll go to the other exponential one. Nah, why not? We'll do the exponential again, just because we're on the same track. So we have an equation which is 2 to the 4x minus 5 times 2 to the 2x, and plus 4 is equal to 0. This is a pretty key type of question you'll need to understand how to solve. I'll let you guys have a think about it if you haven't already seen something like this before. This will be probably tough if you haven't seen it before. And probably even tough to explain as well. But I guess we'll see how we go. Okay, so this one here you solve with a so-called quadratic solution. The way this works is, or at least the way you can identify whether or not you need to do that, is with these descending powers of x here. So if you can identify you've got like a 4x, a 2x, and a no x, or a 2x, a 1x, a 0x, that sort of thing, that's when you know you've got some sort of quote-unquote quadratic solution. What that means is you look at all the exponential terms in your equation and you figure out what the highest common factor of them all would be. And in this case, it'd be 2 to the power of 2x. That becomes your substitution. I'm just going to use u equals 2 to the 2x. And using your index laws or otherwise, you would now have u squared for this, minus 5u for that, plus 4 equals 0. You solve that quadratic, that gives you 2 solutions for u. Just to save some time, I'll just get the CAS to bash that out for me. 331 x squared minus 5x plus 4 equals 0, x. Okay, that did have an easy factorization. Probably should have just done that myself, huh? U equals 1, u equals 4. Now, from there, you've got solutions in terms of u, but we want solutions in terms of x. So what you do is, you at the end, replace your u with whatever it was. 2 to the 2x equals 1, 2 to the 2x equals 4. Then you just solve each of these. So, any ideas what the solutions would be in this case for x?
Would x be 0 and 1?
Yeah, 0 and 1. 0 is going to come from here because 2 to the power of 0 is 1. And 1 is going to come from here because 2 squared is 4. Precisely. Cool. Okay, that's that. So again, how to identify when you do that? It's going to be these descending powers of x's. If you can see multiple exponential terms that have like a common exponential between them, probably your best bet is to do something like this. Okay, next up. We haven't touched circular functions at all for this one right now, so let's see how we go. We have sine of 3x over 2 equals a half. 3x over 2 equals a half, and we're doing it between plus minus pi. So we want to find all the solutions between positive and negative pi. So, does anyone remember at least the basics of how we solve circular functions?
I think you need like the trig table of values.
Yep, table of values, that'll be helpful. Probably more effective would be a full unit circle, but you can use a basic table and then flip things around. Yep. So I'll get that one up for those who haven't memorized it yet. So that'll be apparent on the screen share. I'll even do a screenshot for the chat if you just want to use the chat instead. All right, so that'll be important. How do we start using that? Okay, so the way this works is you first identify what you want to try and do is rearrange your equation to equal some exact value. So you want to have circular function on its own and an exact value on the other side. We already have that, which is nice. From there, identify what is the exact value that appears on the unit circle. In this case, it's a half. So if you look onto the screen share or the chat, you'll notice a bunch of coordinates will have a half on them. You care about the ones that are positive, a half. Now, more specifically, you care about the y values that are a half because you care about sine of theta, or sine of some angle. Sine is always going to be the y component, cos is always going to be the x component. That's just going to be something you have to either have memorized or otherwise know. So, we need to look on the unit circle for where sine is equal to a half. and the only y value that is equal to half is going to be the base angle of pi over 6 or the base angle of 5 pi over 6. Both of those spots on the screen share. I'll keep them highlighted. Now, what that means is everything in the brackets, so 3x over 2, is going to be equal to those base angles. So pi over 6, comma, 5 pi over 6. These could be two separate equations. I just like using commas to minimize the amount you have to write out. That's how it starts. Anyway, find the spots on the unit circle. From there, there's a couple ways you go about it. I recommend in my notes rewriting this domain to actually match what our new domain should look like. Yeah, and so that's what we'll do. So the way that I like to handle this is I take whatever's inside the brackets and I substitute it. So instead of saying 3x over 2, I'm going to say u equals 3x over 2. So basically that means these numbers are now equal to u as opposed to 3x over 2. The reason why we're doing that is because we can now use that to rewrite our domain purely in terms of this u variable instead of some other x variable. And the advantage there is that it's going to make it super obvious when we stop finding solutions. Oh yeah, exactly that, when we stop finding solutions. So what that looks like, you take the x values on the upper and lower bound, you stuff them into this substitution, and then they become your new upper and lower bound. So we could say like u1, the lower bound, is now going to be negative pi times 3 over 2. So minus 3 pi over 2. Same thing for pi. So stuff a pi in there, 3 pi on 2. Hence, our new domain that we're trying to solve for will be between, so u is an element of plus minus 3 pi on 2. That tells us exactly and clearly where to start and where to stop. So, if we're looking at our initial solutions here, they already fit within our domain. Pi over 6, 5 pi over 6, we haven't crossed over 3 pi over 2. So again, if we look to the screen share, 3 pi over 2 is this spot all the way down here. This spot all the way down here. Pi over 6 was up here, 5 pi over 6 was here. We haven't crossed over yet. But what that does mean is that we have already found everything in the positive section. So everything that's been highlighted there, that's where you need to stop. We found everything in the positive direction. But we have a negative direction to worry about. The way negatives work is you basically count in the opposite direction. That's the basics of it. So a negative 3 pi over 2 means from this right hand side going in a clockwise direction, we need to cut off here. So everything that's highlighted there is what is fair game. Now, that means there's only one more spot that we can put on our solution set, and that's going to be the 5 pi over 6 spot, or when it's in its negative form, you would call this negative 7 pi on 6, just because of that flip. So the basic rule of how to figure out if it's negative, well, the negative equivalent is you find the spot that you want and you flip vertically. So the vertical flip will be the equivalent negative of that spot. That's why this is negative 7 pi on 6. So okay, what that means is now we have our solutions, which are pi on 6, 5 pi on 6, and negative 7 pi on 6. That is everything, and we're certain of it, between the domain that we care about. From here, now you can do your rearranging, which just means you plug back in what u was, and then you rearrange to get the x back on its own. So from there, it would just be multiply everything by 2 and divide everything by 3. So multiply everything by 2 just means it's now everything is being divided by 3, because all those denominators get cancelled down a bit. And then dividing everything by 3 will now mean that everything is divided by 9 at the end. So finally, answers are going to be x equals pi on 9, 5 pi on 9, and minus 7 pi on 9. The advantage is now, when you check these answers, everything is now within the domain that you cared about. No more do you have to guess and check to see if I've got to find more solutions in the forward direction or more solutions in the negative direction. you just sort of have that. So again, nothing is between, nothing exceeds that domain. There's probably a lot if you guys haven't seen that before, or if anyone hasn't seen it before. Do I need to clarify anything in there? More than happy to do so. Okay, no worries then. So, yeah, okay, I've got a couple of things we could do. Yeah, let's talk more circular function stuff. So, the next question that is being asked from the book is, we have some function h of x is equal to 5 minus 3 cos pi x over 3, and we're simply told to find the range and period of that function. Range and period. Range being all the possible y values, and period, well, I'll let someone tell me what that's all about. What would we do? That's what the graph would look like, assuming I haven't done anything stupid there. Yeah, I have. That should be a... Damn it. Got those back to front. Excuse me, let me fix that. Goes up by 5, and then plus minus 3 from that. So 8 and 2. That's better. Okay, so the way circular functions work is they are periodic in nature, and they look kind of like a wave. If I were to continue drawing this forever, it would look something like that. So, how do you figure out the overall shape, like I've done there? You identify first the vertical translation. That's going to be whatever the plus is, or the minus, perhaps, at the front or back of your function. As long as it's not like a multiplication on your function, you're sorted. That will set the middle of your circular function. I know it's not great, that's supposed to be the middle. From there, the next term is technically the amplitude. If you just take the 3, this minus is more so sort of as a reflection. This amplitude here simply means that from the middle, you're going to go up 3 and down 3, as far as peaks and troughs go. So 5 minus 3 gets you to 2, 5 plus 3 gets you to 8. From there, I haven't drawn anything x related just yet, but just by drawing that enough, I know that my peaks are going to occur at y equals 8, and my troughs are going to occur at y equals 2. If the range is all the possible y values, what's the range of this going to be?
Including 2 and 8?
Yeah, 2 to 8. Exactly. So, all the possible y values, it can't go lower than the trough, it can't go higher than the peak. Cool. Now the next thing there was the period. The period of any circular function is just how long it takes for that circular function to complete one full cycle in the x domain. It is always calculated by 2 pi divided by n, where n is the coefficient on the x. So everything that's multiplying or dividing, same stuff, the x. So in this case, your n is going to be pi over 3. So capital T is equal to 2 pi divided by n, so divided by pi on 3. Dividing fractions, you just flip it to multiplication. 2 pi times 3 on pi. Pi's cancel. Period of 6. So we know it takes 6, whatever x is in units, 6x units for the circular function to repeat once. And the range, well, that was given by this sort of, the overall shape, peaks, troughs. Anything to clarify there? If not, I'll add my own little bit, which is you can actually find all of these key features, x values, by splitting this period. So we know starts at 0, ends at 6. What we find is that if you split this in 4 equal bits, so 3, 1.5, and 4.5, what we say is that the 3 will be the peak, the 0 will be the trough, the 1.5 and the 4.5 will be these middles. So that's if you want to sketch it more specifically. We only cared in this question about range and period though, but that's more so if you wanted to sketch this in more detail. And right, the reason why it looks like this rather than starting from the top is because of the overall shape of cos and the fact that it's negative. So a bit harder to explain that without a bunch of visuals. So I will bring some up. Okay, so to the screen share now. The very basic cos without anything on it will start at a peak, so x equals 0 becomes a peak, and then dip as a trough. When you have a negative sign applied, everything flips. So instead of starting at a peak, you now start at a trough and end at the trough. That's all that is really. So you have to be aware of what the basic shapes are of cosine and sine. Okay, that's that. Next up, simultaneous equations. Yeah, I'm gonna need more space than that for simultaneous. Okay. Yep. Simultaneous, so we're going to have mx plus y is equal to 2. It's equation 1. And we're going to have 2x plus bracket m minus 1 y equals minus 4. And there's a whole bunch of things we have to do. Namely, we are finding, so, yeah, I'll do it this way. One thing we want to care about is the unique solution. The other thing we want to find is when we have no solution. And the final thing we care about is for infinite solutions. So, before we even get into solving it specifically, does anyone know the criteria for unique, no, and infinite solutions?
Unique has only one solution.
Yeah.
No solutions, as it says, there are no solutions in the two graphs.
Yeah.
Equation, and then infinite solutions basically saying the graph when you sketch it would be the same, but they're both have the same gradient and same y-intercept.
Yeah, there you go. Nice, exactly. So to put a visual to what he was saying there, number one, unique solution could be like this. You have two linears that intersect at just a single point. Number two, no solutions. The only way you get no solutions is with parallel lines. So if these have same gradient, different y-intercept, they'll never touch. And then number three, infinite solutions just means you have the same line overlapped onto each other. So in terms of things that you can actually now solve for, my preferred approach is a y equals mx plus c approach, which means you figure out what does my gradient need to be in these conditions and what does my y-intercept need to be in these conditions. For unique, you will always cross over at one point as long as gradients are different. The y-intercept means nothing. As long as you have different gradients, you're fine. For parallel, you get this if gradients are same. Obviously, it's parallel. and y-intercepts are different. For this one, finally, you want both to be the same because of the same line. So, the reason why this is my preferred approach is because if you do a y equals mx plus c approach, it does not matter what was asked here, you solve it the exact same way. Whereas if you do like a ratios approach, which I might have at least briefly shown at some point, that will be where like you divide, I don't even want to get into it because it only really works well, in my opinion, for unique solution. Well, actually no, for infinite. I forget what's the good one, but point being, it's not super global, in my opinion. So, step 1 in here is to rearrange both of these into y equals mx plus c. So, just get the y on its own, essentially. This one's nice and easy. Y equals 2, well, I could even just say minus mx plus 2. That way it looks super consistent. And then for this one, it will be subtract 2x and divide everything by m minus 1. So y equals minus 2 over m minus 1 x, and then minus 4 divided by m minus 1. Okay, that gives us 2 new equations to work with. Now, doesn't really matter what you're solving for. What you do is you compare gradients to each other in 2 unique equations. Oh, sorry, in their own unique equation, and then you compare y-intercepts to each other in their unique equation. So, I know it'll be off screen for a little bit, but basically going to have negative m equals negative 2 over m minus 1. So this was just gradient of first, this was gradient of second. If you see gradient of first, gradient of second. Next will be these two to equal each other. 2 equals minus 4 over m plus 1. 2 equals minus 4 over m minus 1. We just solve each of these individually. These are both, well, this one's going to be a quadratic, this one's going to be a linear. Let me just solve that first then. That seems easier. 2, m minus 1, minus 4, m minus 1, negative 2, m equals minus 1. So it could be good when you're doing this yourself to label these. So this could be c equals same, and this would be m equals same. So gradients. We're about to go over time. Feel free to leave if you want to. I'll just finish this one up for everyone who wants to stay. From there, you solve this one as well. So going to have minus m bracket m minus 1 equals minus 2. This is some quadratic. You guys know how to solve quadratics. I'll just cheat real quick. 3, 1, x. Well, actually, it's minus x. Minus x times x minus 1 is equal to minus 2, x. Okay, negative 1 and 2. M equals minus 1, m equals minus 2. These are the solutions for gradient same. These are the solutions for y-intercept same. So, if you want to have unique solutions, all you care about is that gradients are different. So, the answer for unique solutions is going to be m is an element of all real, excluding those. Because this is where they're the same. If you want them different, you exclude those. Minus 1, minus 2. So that's for unique. Now, for no solutions, you want them to be parallel, which means you want same gradient, but you don't want same y-intercept. The only thing that achieves that will be m equals negative 2. Because if you choose minus 1, they become the exact same. So for no solution, m equals minus 2. Only possible. For infinite, I gave it away. Those are identical. For infinite, m equals minus 1. So regardless of what the question is asking, do the same thing, get the answer for literally all of them. Yeah, that's about it there. Alright, that does bring us to end of class. If you want me to clarify that, feel free to stay behind. Otherwise, I'll let you enjoy the rest of your day. Take care, guys.